Suppose we have a mass, point-like mass M1 here, and another point-like mass M2 here. And let's say we hold mass M1 stationary. Alternatively, we just move the masses apart in some way along a straight line, and we'll call that straight line a radial line from M1 through, a line through M1 and M2. We're going to call the line in this direction the R-axis. We want to know the change in gravitational potential energy as we move from a distance R1 to a distance, let's cut it off right about here, R2. So we want to move these masses apart so that the separation increases from R1 to R2. And we want to find the change in gravitational potential energy. Okay, well, the gravitational force is negative big G little m1 little m2 over r squared when we are at coordinate r on this axis. The work, well, to get the work from here to here, obviously this is not a constant force. We're going to have to integrate, so we develop the integral. We partition the interval from big R1 to big R2, so we have big R1 equals R0 less than or equal to R1, less than or equal and so forth, less than or equal to R sub n equals big R2. On a typical subinterval, if this is the ith subinterval, I don't have room to write out subinterval, it's going to have a sample point that we're going to call r sub I star, and the interval is going to run from r sub I minus 1 to r sub I with r sub I star in between those two. The gravitational force sub I is then going to be negative G m1 m2 over r sub I star squared. Remember, r sub I star is the distance from, well, the separation, the position along the r-axis within the ith, at some point within the ith interval. And if these intervals are very tiny, the gravitational force is not going to vary much between those 2 points. Okay, well, this means that the work done by gravity on the ith interval is the force times the displacement. Okay, well, the force, and we can tell by the negative sign, the force is in this direction. If we assume we're partitioning, let's assume that R1 is less than R2, so that we're partitioning from the lesser to the greater radius, so that our partitions move in the positive direction, so that the work done by the gravitational force on the ith interval is the force of gravity on that interval times the delta r on that interval. And that equals then negative big G m1 m2 over r sub I star squared times r delta r sub I. Well, that, a miracle occurs, etc. We approach a limit as usual. We sum these up, we approach a limit, and we get then the integral from big R1 to big R2 of negative G m1 m2 over r squared dr, and that equals G m1 m2 times 1 over R2 minus 1 over R1. Now let me be careful, because I had a negative here and I'm not as young as I used to be, so I can reverse things a little bit. Let's kind of check out and make sure this makes sense. So the work done by gravity as I move away is negative, because gravity's pulling this way and we're moving this way. So if R2 is bigger than R1, this had better be negative. Well, it is, because 1 over R2, I've got it wrong. There's another negative sign. I've got this negative. I've got the negative from the antiderivative, so it should be, I got too fancy for my own good there, and this is why I stop and check and why you need to do it too. Okay? So it's 1 over R1 minus 1 over R2. So checking it out again now, if R1 is bigger than R2, then the reciprocal of R1 is less than the reciprocal of R2, making this negative. So now we see that this agrees with the sign of the work done by gravity. So that change in potential energy, which is negative of the work done by the conservative force, gravity being the conservative force, is big G M1, M2 times 1 over R2 minus 1 over R1, the expression I wrote down before when I shouldn't have. Okay, that's your change in potential energy. And then the potential energy relative to infinity would be, and see what I did in the integral here? I hope I didn't mislead you there. We're integrating from R1 to R2. Potential energy relative to infinity, R2 would be infinity. We'd go from R1 to forever, and you might think that would give you an infinite result, but it doesn't, because in the limit as R2 approaches infinity, reciprocal of R2 approaches 0, and we just get negative G M1 M2. I'm having a rash of writing the wrong subscript here. Multiplied by 1 over R1, or just negative G M M1 M2 over R1. Okay, so these are the relationships that we want to use in calculating potential energy of, say, orbiting objects.